So now we're going to work on the subarray sum equals k algorithm. So imagine this. You are a software engineer at an online payment processing platform like Stripe. Your team builds fraud detection for credit card transactions. The system must monitor customer purchases and detect any unusual patterns, like a burst of charges that sum up to a specific suspicious amount. Say, for instance, $2,000 within a very short and specific time frame. Let's think like an engineer and look at the inputs, outputs, and constraints. So, in terms of input, you have a list of transactions that were made by a user over time. And as you can see here, you have a list of transactions, and you can take this list as a list of transactions in a specific window of time. Now, in that specific window of time, we have a fraud threshold of $2,000. The output that we're looking here is that you're going to return the number of continuous time windows or subarrays where the total transaction sum is exactly $2,000. So let's look at the constraints here. And you can see here at the top that we have this constraint, which we're going to translate into the context of the example we're working on. So what that reads is that we are analyzing at least one transaction, but maximum 20,000 transactions. The algorithm must stay fast even if there are 20,000 entries. Constraint number 2 is that we are looking at refunds or reversals, meaning each transaction could be as low as negative 1,000. And of course, we're looking at purchases, meaning each transaction could be as high as $1,000. And constraint number 3 simply means we're checking for any number between negative 10 million and positive 10 million. Remember, fraud systems must handle both refunds and charges. If someone suddenly has a $2,000 worth of charges in, say, 3 minutes, that's when you might want to flag it. And also remember, if you have minus $5,000 in rapid refunds, that's also suspicious. Let's start with the brute force approach, which is a bad idea at scale. So first we're going to create a function called count suspicion bursts that takes a list of transactions and a target amount that we consider suspicious. We're going to start with 0 suspicious patterns found so far. The counter increases when we find one. We're going to check all transactions until we have checked all possible starting points for a suspicious pattern. Every time you start from a new position, you reset your total. This will track the sum of transactions as you expand the window. Then we move forward one transaction at a time, stretching a window from start index to end index, adding more transactions to the total. If the total has reached the fraud threshold, we increment the suspicious window count by 1, and after checking every possible window, we return the final count of suspicious bursts. So let's go ahead and look at Python code. So let's get started. The first thing I'm going to do here is import a list, and then I'm going to create a list of transactions and define k at 2,000. Next, we're going to create the count suspicious burst function that takes a list and the threshold as parameters. Next, we're going to start with 0 suspicious patterns, and the counter will increase when we find one. Next thing we're going to do is check all transactions until we have checked all possible starting points for a suspicious pattern. And every time we start from a new position, we'll reset our total, and this is going to track the sum of transactions as you expand the window. Now we're going to move forward one transaction at a time, stretching a window from start index to end index, adding more transactions to the total. Now, if the total has reached the fraud threshold, we increment the suspicious window count by 1. And after checking every possible window, we return the final count of suspicious bursts. You can pause and implement this and make sure to practice your inner dialogue. Now that we have this, we can simply print the result of the function call like so. And in this case, we should have 4 suspicious transactions, because in this case, this running total, whether it's equal or greater than the fraud threshold, will then yield how many windows we have that exceed the $2,000 threshold. Please go ahead and test. I want to also remind you of using pythontutor.com so that you can learn the execution of the code. And this will make it very, very easy. So let's go ahead and take a look. So as you can see, we start with the list of transactions, we define K, then we call our function. Then as you can see here, we initialize the suspicious window count at 0, and I have a typo here, so make sure you fix that on your end. And then we have the start index at position 0, we have the running total at position 0, we have the end index at position 0. Now we know that position 0 is 500, which means that our running total is not greater or equal than the threshold, so we go back to the loop. And then we keep adding the totals. As you can see here, now the running total at end index 1 is 500 minus 200, so it's 300. And if we keep going here on all the indexes, it's going to get to a point that at end index 3, we do have the running total being 2000, which is greater or equal than the fraud threshold, at which point we are going to see here our suspicious count increasing by 1. And we keep going until we go through index 4, in which the running total is just 1700, and then we go to the last one, in which the running total is 2700, meaning is greater or equal. So that means that our suspicious window count now increases by 2. So if we keep executing this, then we're going to check the next window, in which the start index is going to be 1, meaning we're going to start here at 200. And then the whole process starts again. And I'm just going to keep going here and skip over to the end, because at this point you should have a good sense on how this logic executes. And almost towards the end, as you can see, the suspicious window count is at 3. If we keep executing this, you're going to see that at some point when the end index is 5 and the start index is at 2, meaning it's another subarray within this subarray, you see that we are at 2400, and at that point our suspicious window count goes up to 4, and then we keep going until we run out of things to check, which is going to be at the end where the start index is finally 5. And as you can see here, now the start index is 5, and we go through the final steps, and ultimately the program finishes and we return 4, which is the amount of windows that are equal or exceed the threshold that we have set here. Very important. I recommend that you go through Python Tutor and really understand how the code executes. Trust me, this is going to go a long way. I'm not going to show this on every video, but I am always going to give you the reminder to go and really learn how the code executes. So now that we have implemented the algorithm and seen the code running, it is very important to understand why brute force is a bad idea at scale. So we have 20,000 transactions that we are comparing against each other over and over again with a nested loop. So what we're saying at this O of n squared in terms of time complexity is that we are performing about 400 million operations. So an online payment processing like Stripe handles billions of events. And this approach would flag the transactions too late. It would waste compute resources and it could increase fraud losses due to the lag. Remember, an engineer would call this unscalable, and just because the code works does not mean it's usable. If you look at the time and space complexity, well, we know that it's really cheap in time because we're just tracking counters and there's no extra memory used. But time is extremely expensive because we have two nested loops that check all pairs start and end of transactions. Now it's time to look at the optimal solution, which is to use a hash map. Because here we're going to define a function that checks how many blocks of transactions add up to the fraud threshold. We're going to keep a counter here, so every time we find a valid pattern, we increase the counter. And we're going to add up the transaction amounts as we move through the list, and this is our prefix sum or total so far. We're going to use this dictionary or hash map to remember how many times we've seen each total so far, and we're going to start with O column 1 to account for any subarray starting at index 0. And then we're going to go through each transaction one by one, and we're going to add the current transaction to our total so far, and now figure out if we have seen a total before, such that subtracting it from the current total equals the fraud threshold. That means the subarray between then and now is suspicious. If that required total was seen before, then we found one or more valid subarrays. We add how many times we've seen it to our count, and we record that we've seen this running total. If this is the first time, we start at 0, otherwise we increment it. And ultimately, we return the total number of suspicious subarrays found. This is our final result. So let's go ahead and look at the Python code. So for the optimal solution, I'm going to start by importing the list type, setting up the list of transactions K, setting up the function, and I already have here the print of our test. So let's go ahead and start doing this. So first, like we saw in the pseudocode, I'm going to set up the suspicious count to 0, and we're going to also initialize the running total to 0 here. And then I'm going to create the hash map of the prefix totals seen, and we're going to initialize it like this. Then we're going to loop through each transaction in the list of transactions. We're going to keep a running total, and also we're going to keep the required total, which is the running total minus the fraud threshold. Then we're going to look at the suspicious count, and basically what we're going to do here is simply check if that required total has been seen before. And then we found one or more subarrays, and then add how many times we've seen that total in our count. Then we're going to record that we have seen this running total. And if it's the first time, we start at 1, otherwise we increment it by 1. And lastly, we return the suspicious count. And since this is the same example here, I'm going to run it. And as you can see, in this case, we only have 1. And the reason we only get 1 is because in this one, we are strictly checking that it is 2000. We're strictly checking the fraud threshold, unlike the brute force one, where we were looking at anything greater or equal. But if I change this to equal, then it also yields only 1. And I'm just going to clear here so you can see it clearly or clearer. And as you can see, if I change that logic here, it also only yields 1, because this time around, we're just being more strict in only finding the 2000 mark. So here you can pause, implement, and then I do recommend that you open pythontutor.com and check the program execution. Let's discuss why this scales like a pro. So your Stripe, you monitor a list of user transactions to detect suspicious bursts, continuous chunks of purchases that add up to exactly a fraud threshold, which is in this case 2000. And our input, as we know, is the list of transactions, and the fraud threshold is 2000. So now imagine, instead of checking 6 transactions like we just did, imagine we had 6 million. Now let's analyze the algorithm. So as you can see, all the operations inside of the loop, which is O of n, are of constant time. So this makes our algorithm O of n. It'll grow linearly as the input grows. Now in terms of space, we're also looking at O of n, because we store prefix sums in a hash map, and in the worst case, every running total is unique. That means we store 1 key per transaction. So once again, we're looking at O of n in time and O of n in space. Now the trade-off, time versus memory, just like we saw in the previous problem, we have time, O of n, for brute force. However, the space is O of 1, which is very cheap. But in the hash map solution, the time is much faster. It stays O of n, it's linear, but we do need to use more memory. Now, in terms of engineering mindset, remember, you're tracking user transactions to detect suspicious spending bursts. And thanks to prefix sums and hash maps, you only need 1 pass, and you remember just enough to move fast. No backtracking, no nested loops. Your system scales to millions of transactions per minute and still runs in real time.